So in this video, we're going to talk about two-dimensional motion, just an introduction to it, and then we're going to focus in on vectors and how we can add and subtract vectors, which is critical to analyzing two-dimensional motion. So to this point, all that we've been analyzing is motion in one dimension. That means that the motion was all in the x direction, and we also did like free fall, which was all in the y direction. But now we're going to consider what happens when something moves in both directions, like combined. So something like like a projectile, so like a ball flying through the air. And so we can see that with this is actually moving in the x and the y at the same time. And so we're going to just build the components for this, or the pieces that we'll need to analyze this. And basically we'll be breaking things down into the two dimensions through which it's moving and deal with them independently. So in this case, we would deal with the motion in the x and the motion in the y. So that's kind of where we're headed. But to get there, we got to be able to start thinking about vectors and how we can add these things together. Okay, so let's just dive right in. So there's two methods, and what we're going to focus on again is going to be adding and subtracting. Keep in mind, subtraction is just adding. It's adding the negative. So these are the same thing, adding, subtracting. Well, they're very similar. Vectors. And there's two methods. There is the graphical method, which I'll talk briefly about. You can read your text for more detail. And then there's the analytical method. Analytical method, which I'll spend more of the time talking about. Okay, so what's the graphical method? So the graphical method is just how we draw it. So remember that vectors have both magnitude and direction, and we indicate that with an arrow. So let's say that I had some vector, just some random vector like this. So we'll call it vector A. Now, if I wanted to add it, what we do to add, we put it head to tail. So what's a head and what's a tail? You could probably figure that out, but I'll go ahead and label this. On a vector, we call this the head and this the tail. So if I wanted to add, say, A plus B, then I would just move B, or I would just place B with its tail to the head of A. And this would be vector B. And so what this is showing is A and B, and then I'm going to add them. And to add them, all we do is draw a vector from the tail up to the head of the other one. So it would be something like this. And this vector here it's called the resultant vector. And that's, we could call it like R, and that would be equal to A plus B. Now be careful here, please don't fall in this trap. This is vector addition. This is not like a triangle, because when we draw a right triangle, the vectors look like it's just we add up the sides, but we know that's not true, because we know that in a triangle, well, it's true for vectors, but that doesn't mean that you got to keep in mind there's the Pythagorean theorem, so we can't just go on the magnitude, because direction is in here somewhere, okay? So just be careful. We're not breaking Pythagorean's rules, because this is vector addition. So to add graphically, all we do is put them head to tail. That's it. And then draw from the tail of the first one to the head of the second one. Well, what if we were subtracting? So keep in mind that, there's two methods. I'll show you my preference, what I do. So for subtraction, and graphically again, subtraction. If I have A minus B, that's the same thing as saying A plus negative B. And so what we're going to do is we're just going to add the opposite of my B vector, of my second vector. So what does the opposite mean? All it means is that we flip the direction. So in the same case with these two vectors, instead of adding them, say I wanted to subtract them. So I wanted to do A minus B. then I would just flip the direction of B. So we would end up with something like this. This would be A, and then we would change the direction of B. So we would flip it so that it's directly opposite of what it was before. So this is negative B. So you see what we're doing is we're just adding. It's head to tail. And so my resultant vector would be down here. This would be the resultant, which is A minus B, or A plus negative B, however you want to say it. For graphical analysis, order does not matter. If I added B to A, so I did B first and then I did A, I would get the same resultant. So it's commutative. A plus B equals B plus A. All right, again, you can go and you can read more about the graphical method. We don't use it as much, but it lays the foundation for what we really want to do. And that's the analytical method. Analytical method. So, oh man, I cannot spell today. Okay, so suppose we're doing the same thing. So I'll just draw the same kind of thing. So like A plus B. Okay, then what we're going to do is we're gonna break this into what we call vector components. We want to use vector components. And vector components are the things that make up the actual vector. And for our case, since we're working in 2 dimensions, I'll go ahead and draw a coordinate system on here. So we'll do the Cartesian. We'll just put that vector A right at the origin. So X and Y. So what I want to know is the vector components are the pieces in each of these directions. So like what piece of A is in the X direction and what piece of it is in the Y direction. And then the same thing for B. We figure out the X direction and the Y direction. And then we can just add up the X's and Y's. I'll show you an example and that will make more sense. And then we can put it all back together and it creates our resultant for us. And so what we do is we just think we're going to break this vector A, I'm going to break it into its 2 components. And so I can see that like to get from here, from point, say 1 to point 2, I could go along this line, or I could move along in the X direction. So I could go, you know, so many units this way until I'm right below it. And that would be my X direction. And we can label that as A in the X direction. So a little sub X. And then I would just turn north or turn along the Y direction, and then I could go up like that. And this would be A in the Y direction. So these are the 2 pieces, and notice it forms a right triangle. And so we can figure out these sides pretty easily. If I know the magnitude and I know the angle, we can use trig. This is why we started the year by talking about trig, but this is really where it's going to come into play. Likewise for B, I could do B in the X direction. So B would start here, and I would go over a couple, and then we would go up. And then again, we would call these, you know, this would be BX and BY. And the cool thing about this is that if I move this BX down, so what I'm going to do is I'm just going to take this vector and I'm going to slide it down here, and I'm going to put it right here. So this is just BX. All I did was slide it down. And then I can do the same with this AY. I'm going to slide it over. Then what you'll see is that if I draw a triangle, this picture is getting a little busy, but hopefully you'll be able to see it. And I'll kind of highlight it. What we have is a big right triangle from adding the vectors. So you see the big red one, which is made up of the sides AX plus BX and AY, I didn't label it, AY plus BY. So to add vectors analytically, we can just add the components. And then we can figure out what the hypotenuse of this triangle is, or our resultant vector. That's the idea. So we break it up into X and Y pieces. They're called components. We add them together, and then we get our resultant. So what does this look like mathematically? Well, there's a couple of things we would say. Number one, any vector can be broken into, and this is just 2 dimensions, into its 2 dimensions is equal to ax plus ay. These components add up to be this vector. And then the resultant vector, so in this case, so I would have 2. So then we would have b is going to be bx plus by. The vector, not the magnitude. The magnitude would have to be the square root and Pythagorean and all of that. So in order to add these, in the previous, graphically, we said, well, the resultant vector is equal to these 2 vectors, a plus b. So when I have the components, what we can do is we can just add up the pieces. So the resultant would be ax plus bx plus ay plus by. So we would just add up the 2 pieces and then we could figure out the total. But you have to be careful. We can't mix x's and y's. And so one of the things we can do is we can add this new notation just to indicate the direction. And so I would say x and we say hat. And over here this would be y hat. So this is called vector notation. Vector notation. I'll do an example here in a bit so that you can see what it looks like with some numbers. Vector notation, we use this x hat and y hat. And all that means is that we're going to go this much in the x direction and this much in the y direction. So these 2 things just indicate direction. Indicate direction. That's all they mean. All right, so let's do an example. Let's say I'm just going to kind of keep it the same. We'll say A has a magnitude of like 10 meters. B has 5 meters. I know these I didn't draw them correctly, but I need some room. The B vector is 5 meters, so it should be half the length of this one. But I'm just trying to get an example, and again, I need some room. Now, if you think back, well, let me get a coordinate system on here. But if you think back to the trig, we don't know what those sides are. We need to know an angle. You can't tell what it is just from one side, just from knowing the hypotenuse. And so we have to put some angles on here. And let's say that's, I don't know, 20 degrees. And then this one, remember, is measured this way. So let's say that's, I don't know, 50 degrees. So basically we're going 10 meters at 20 degrees and then 5 meters at 50 degrees. We can now figure out our pieces. So we could figure out AX and AY from trig. So AX and AY. Likewise, we can do it with B. So we could do BX and BY. I'm just drawing it so that you can see the relationship here with the angle. But I'm going to write everything over here. So one way of doing it, so let's just do A. So the A vector. So AX, if you go back and review your trig, what you'll see is that this one right here is the magnitude 10 times it's next to the angle, so it's cosine 20. And AY is the magnitude 10 times sine 20. For the B vector, we'll get Bx is going to be the magnitude 5 times cosine, because it's next to the angle again. So we would get 5 cosine 50, and By equals 5 sine 50. And that's from trig. So what's our resultant? So, and you could get numbers here. I'm not going to bother with that. But our resultant vector, the total, would be A plus B. But we have to deal with components. So it's going to be AX plus BX, and that's in the X direction, plus AY BY plus BY in the Y direction, so Y hat. And now we just substitute. So we get 10 cosine 20 plus bx, 5 cosine 50. And that would be in the x direction. And likewise in the y. 10 sine 20 plus 5 sine 50 in the y direction. I'm going to pause and calculate it. So when you calculate that, what you get is a little, about 12.5 in the x direction and then 7 up. So it's going to go 12 this way and then 7 up, and that would be my resultant vector. This from the origin all the way to the head of B. But that doesn't tell us enough information about it. Now we could work with this, but what we wanted to be able to do is get the magnitude. Like if I draw the vector itself, what's the magnitude and what's the angle? We know we know the pieces now. We know the x component and we know the y component. So we want to be able to put it back together. And so to do that, I'm going to redraw it. So if r is like this, that's my r. And then we would have rx this way and ry. And please don't get lost in notation. This is rx in the x direction. And then that would be at some angle theta. So to get the magnitude of the vector, how long it is, that would be the Pythagorean theorem. And so we would see that r, the magnitude of r, so how long it is, squared is equal to rx squared plus ry squared. And so if I to get rid of the square, I would then take the square root. So it would be the square root of this squared plus this squared. And that would be the magnitude of the vector. So if we calculate that real quick, we get 14.5. So if I go 12 this way and 7 this way, that would be the same as going 14.5 along here. The other thing we want to do is be able to figure out this theta. And I typically will use ry and rx because that's what we're solving for, and so it just makes it convenient. And so if I relate this angle, that would be the opposite, and this is the adjacent, and so that would be tangent. So tangent of theta would be ry over rx, which is solving for theta, we would get theta is going to be inverse tangent of that ratio, ry to rx. And again, calculating for that, we find that theta is 29.896 degrees. And so now we've fully solved it. We know the magnitude and the direction of the resultant vector. So anyway, you can refer back to your book. There's more examples. I think I have an example video. You can check my channel. But we'll be doing this a lot. And typically it's, we'll define this stuff, and then we're going to tie it back into, displacement and velocity and all of that stuff. And we'll be doing more of this than we do graphical. So that's vectors.